wanted to talk about the TCP timeout. So remember that when the sender sends packets out, he expects an acknowledgement by a certain time. And the question is, how does he detect if the packet is lost or not? Right? So one way to do that is that you have a timeout. So when you send the packet, you set a timer with a certain timeout. And if you don't get an acknowledgement by that time, then you assume that the data packet was lost and you can retransmit. Okay, so suppose this packet was lost or the ACK was lost. What you would do is this timer would expire because you didn't get back an acknowledgement, and you can retransmit. Okay. So retransmit if there is no acknowledgement received for this particular packet. Okay. So let's say this ACK or even the data packet got lost, you would retransmit. So the question is, what should this timer value be set to? Okay, and so one of the difficulties is that suppose this is the sender and this is the receiver. This TCP protocol should work for any pair of sender and receiver. So anywhere in the internet. So if your sender and receiver are next to each other, let's say in the lab, you can expect the acknowledgement to come back really fast because the round trip time is really small. But if they're at the other ends of the internet, one, let's say it's in North America or something like that, one, and the sender is in India, then the round trip time could be quite high. Of the order of hundreds of milliseconds. Okay, so this RTT can vary by orders of magnitude. Okay, and what you want to do is you want to set your timeout value somewhat related to the round trip time, maybe a little bit higher, and you don't want to unnecessarily wait for too long. Okay, because if your timer is, say, extremely large compared to the round trip time, you could have detected the packet loss much sooner and you're sort of not sending it. Unnecessarily you're waiting for too long. But if your timeout value is too small, then that's also a problem, that even though the data was in flight and you were going to get back an acknowledgement, unnecessarily you said that there is a packet loss. Okay, so this is a question that they had to answer, and so the protocol that you're going to put is the same. It's there in your operating system, so it should work for all sorts of cases. Okay, so one issue is RTT varies by orders of magnitude. Across network paths. A second issue is that the RTT actually varies with time. So even if it's between the same sender and the receiver, the RTT could vary a lot. And why is that? So if you do something like even a ping between two nodes from the sender to the receiver, you will notice that the RTT might look something like this. There may be some minimum value and beyond that there is some observed RTT lengths. Sometimes it comes down to the minimum and sometimes it's much higher. So why is that the case? Well, if you look at a network path, say this is the sender, these are the various routers. and I zoom into one of the routers, we see that there are these queues, and packets might end up in these queues just because there is some amount of congestion. So if all queue sizes everywhere on this path were 0, you would get this minimum delay. And of course, for the round trip time, we are measuring, maybe in the most general case, you would have potentially even another path back to the sender. Okay, so data may be going this way and the acknowledgements are coming this way. So if all the queues along this path are empty, then you would see this sort of a round trip time. Whereas if the queues start filling up anywhere on this round trip path, then the round trip time delays are going to go up. Okay, so this is due to queuing delays. And this delay is due to speed of light and what is called the transmission delay. So in earlier classes we've discussed what this transmission delay is due to, and essentially that's because of the store and forward protocol or store and forward method used by these routers. Okay, so you don't transmit a packet as soon as the first few bytes come in. You wait till the entire packet comes in before putting it in the output queue. Okay, that's store and forward, and that adds a little bit of extra delay. Okay. So this is what the RTT looks like, and in this sort of a situation, what should you set the timeout to? Because if you set it equal to the min RTT, then there's going to be a problem that quite often the RTT is larger than that, and unnecessarily you would retransmit the packet, right? So you would have to take this variability for the same path. Okay, so this first point is for I'm saying the RTT varies across different network paths. Okay, so there could be machines close to each other or far from each other. So effectively what I mean is that the speed of light delay could be very different across different network paths. So TCP has to work for all of them. The second point is related to the same network path. That for the same network path, even if the routers are all the same, the RTT varies a lot. So these are some issues, and of course there are more complex issues, that what if the path changes, that some network protocol, the routing protocol might choose a different path somewhere. Maybe the interior gateway protocol chooses a different shortest path, or there is some BGP decision where because of which you take a different route. So it's possible that the network path itself changes in between for the same TCP flow. So we'll of course exclude that those complications for the time. So there are yet more issues, and the thing is, what if there are packet losses? Then, like the problem I think which was there in the mid-SEM. So suppose you send out a packet, right, and let's say this is packet N, and the timeout expired, and you retransmit the packet. And after this you get back an acknowledgement. So can you use this to measure the RTT? This is an issue, and it's a little bit tricky because what if the ACK was actually triggered by this? So is this the ACK, or did this first attempt create the ACK, and maybe there was excessive delay in the network and this ACK came back? Okay, so can we measure the RTT for these sorts of situations? Okay, so let's see what exactly they decided for TCP. Okay, so first let's look at the old algorithm. Which was used when first TCP was developed. So what they said is is that we cannot just take any single RTT measurement. We somehow have to sort of try to calculate the average round trip time. Okay, so you can't take the minimum round trip time or just a single measurement. We are measuring the round trip time when you're sending data and getting back acknowledgements. Okay. And let's try to get the average round trip time. So how do you calculate an average? So you're getting measurements of the round trip time like this. Okay, so this is time at which we are sending out packets. So you're sending out different packets and you're getting back acknowledgements, and that is giving you a measurement of the round trip time. So when I say average, okay, what is the average? Because at this point in time, suppose we are here, this is the present time, we have sent out a packet and this is the round trip time we have measured. Should we take the round trip time averaged over this entire time period from the beginning? What should we do, right? And suppose we have reached this point in time, if we want the average, should we take the average here measured across all of this? And you would think, yes, why not? But the question is how to do that computation easily. Okay, I mean that's something to think about. So what if there are also some some sort of a temporary increase in the round trip time? So suppose this is the time and this is the measured RTT. So suppose this is the minimum round trip time, it was like this, and then suddenly the RTT goes up because of some congestion. So does it make sense to measure the average all the way from the beginning up to here, or should we give more weightage to the most recent past? Okay, so this is something that they were thinking about. So what they said is that we will make the RTT measurement for every packet, okay, every packet sent out, and let's call that the sample RTT. So this is the most recent RTT measurement. So what they said is we will get the estimated RTT which is going to be a weighted average of the previous estimated RTT plus 1 minus alpha times the sample RTT. Okay, so this is trying to capture the average. This estimated RTT is something like a moving average, right? So the thing is, this is sort of like something not exactly the average, but like an average, I would say. And you're updating that average based on the current measured round trip time. Okay, and alpha is parameter between 0 and 1. So what does this mean? So suppose alpha is equal to close to 1. What does that mean? It means that I am giving very little weight to the current measured round trip time. Okay, and I am giving more weightage to what I measured in the past. So I am giving less importance to the current measurement. And if alpha is close to 1, let's think what would our estimated RTT be? It would be something like this, and it would slowly increase. So this could be an issue because we are not tracking the sudden increase in the round trip time over here. Okay, if we finally we are going to set our timeout value based on this estimated RTT, and that timeout value may be too low in this case just because we have set alpha to be very high. But suppose alpha is close to 0. So the other extreme. So in this case we are giving a lot of importance to the recent measurement. So what would happen in that case? Well, so in this case the estimated RTT would track the measured RTT, okay, and it would be something like this, which may be good in this situation, but there may be other situations where it's not good. So so let's say over here, for example, let's say that the RTT has come down, and or there may be a spike, let's say like this. So in this sort of a situation, if there is a spike over here, there is a problem now in that we would have made estim RTT quite low here, and now when the RTT suddenly increases, we are not prepared because our timeout value would be too low, and unnecessarily we would say that the packet is lost when there was just a sudden increase in the RTT. So there's a trade-off. What should this alpha be? Okay, and we'll see what values eventually, or the recommended values for alpha just a little bit later. So in this first algorithm, they chose timeout equals to twice the estimated RTT. So this is computationally quite easy to do, right? We're just taking a weighted average of these two, and in fact, if you choose appropriate values of alpha, you can do a better job, right? If it's something like a 1 over, it's of the type of 1 over 2 to the power of, let's say, m, it might be easier to do this computationally, because if you divide a number by 2, it is just shifting of the bits, right? Divide or multiply by 2, right? So they had planned, of course, assuming that lots of packets would keep coming in and going out, and you don't want to do a heavy computation every time you get an acknowledgement, right? Because then you're going to use up a lot of resources on your machine. So this was the original algorithm, but they improved it given all these issues that we had talked about, right? So you may have situation where the RTT is varying a lot, and maybe we need to do something better for these sorts of situations. So what is done currently, so we take variability into account, in a more explicit fashion than was taken over here. So this estim RTT is just going to track somewhat what the mean is. Okay, but they said let's do something more than that. So suppose I give you a Gaussian distribution. So this is just a typical probability distribution, a Gaussian distribution, and this is what the mean would, this is, let's say, the mean in the middle, and you have some standard deviation. So suppose the RTT had this distribution. Of course it probably won't. I mean, a Gaussian distribution first of all can go negative, and you're never going to have an RTT that is negative, right? So this is not a exact, this is not a very maybe perfect example, but suppose you had an RTT distribution which was like this, right? So what I mean is, you send out a packet and the round trip time comes from this distribution. It's mostly around this mean, but sometimes it could be quite large. Or what would you set the timeout to be equal to? So your timeout has to be larger than most observed RTTs, because if it is less than that, then you're saying that there was a packet loss when there actually wasn't. Okay, and so what would you do here? If this was a distribution, you would take 3 standard deviations, let's say, and I would say that the timeout, I'm going to set the timeout equal to mean plus 3 standard deviations. Yeah, and then you can show with 3 standard deviations, most of the time this the measured value from this distribution is going to be less than this. Okay. So what they said is, let's use this estim RTT to give us some idea of what the mean is, but let's also try to get an idea of the standard deviation. And essentially the idea is, of course they didn't exactly do this, that you want to set timeout equal to mean plus let's say some m times the standard deviation. Okay, so this was the idea that they had. So of course they do the same thing. So measure estim RTT as before. But also what we are going to do is, we are going to measure something called the deviation. So let's call it a diff. Diff is equal to sample RTT minus the estim RTT. Okay, so of course we don't exactly know what the mean is, but we are assuming this is the mean. So what is this? So this is the difference between the measured value and the mean. Okay. So effectively what is this doing? So suppose you had measurements from a distribution. Suppose x1, x2 and so on up to xn are let's say let's say some values from random variable x. Okay, so you repeatedly, let's say, choose a random value from this particular some particular distribution. Okay, and let's just assume that they are IID. So what is the standard deviation? Okay, so first of all you would get the mean, estimated mean is just equal to 1 over n xi, and standard deviation, measured the standard deviation, is going to be square root of 1 over n xi minus x bar whole square, right? So this diff is giving us one of these measurements. Okay, you're sort of like xi is sort of like the latest measurement, the sample RTT, and you're subtracting it from the mean. Okay, so this is something like xi minus x bar. Now suppose we wanted to calculate the standard deviation, we would have to do this. We would have to square and take the average and the square root. So that is a bit of a pain to do, right? You have to square and take the square root and so on, and every time you get back an acknowledgement, you don't want to do this. So instead of looking at standard deviation, what they looked at is something called the mean deviation. So what is the mean deviation? That is equal to 1 over n, I is equal to 1 to n, xi minus x bar. Okay, so here this is not the standard deviation where you square and take the square root, you are just taking the mod of the current measured value minus the mean value, right, and you're taking the sum of all of those, or the average of all of those. So they said let's go with this. So what TCP does is the following: they calculate deviation. So this is the deviation is equal to the previous value, okay, multiplied by 1 minus beta plus beta times mod of the diff. Okay, so this quantity is trying to give you the mean deviation, but of course it's doing it in a moving average fashion. It's not recomputing everything from the beginning. Okay, it's not doing this exact calculation. It's looking at the previous value, and of course it's giving a certain weightage to this particular diff over here. Okay, this is the current, this is the most recent deviation. Value. Okay, so this is what we do, and let me just, okay. So what is the final timeout? So the timeout is equal to mu times the estimated RTT plus phi times the deviation. So we are trying to make it look something like this over here. We want to have mean plus m times the standard deviation. Of course, we replace the standard deviation by the mean deviation. So typically you would choose this is equal to 1, and this is chosen to be 4. So these are the recommended values, but of course if you want you can go and change these values, right? TCP can be changed. So finally, what are the values of alpha and beta? So recall that estim RTT is alpha times estim RTT plus 1 minus alpha sample RTT. So what we do is, these are the recommended values. Alpha is 7 by 8, so this would be 1 over 8. Okay, so we're giving most of the weight to the average, but a little bit 1/8 is given to the current measurement. This is for the calculating the mean, and the beta value is chosen to be 1/4, where beta is used over here when we are calculating the deviation. Okay, so we give 1/4 weight to the most recent value and 3/4 to the previous measured value. Okay. So this is how we normally calculate timeout in TCP. So what about the other issues that we had discussed? So what we have looked at till now is we have looked at this variability, and we've sort of taken into account this queuing delay. We've sort of measured the mean, what it's going to be like, and we looked at mean deviation. Okay. And of course, from our measurements, we are going to be able to deal with a lot of RTT variability. I mean, so even if the RTT is large, what we are going to do is we are going to measure that it's large, and we would set the timeout value appropriately. And if the RTT is small, our measured values are going to be small, so we set the timer values lower. Right? Of course, initially we have to set some timeout value which is reasonably large. So that would be set larger than most expected round trip times you would see in the internet, right? Because you have to plan for a worst case. You don't want to set the RTT initially to be too low, because then unnecessarily you will say that there is a packet loss and you assume congestion, and then you take a lot of maybe negative, you do congestion control, you decrease your data rate and so on, right? So your initial timeout value is going to be large, but subsequently as you measure this round trip time, you'll get better ideas of what the timeout is going to be. What about this issue that packets may get lost, right? And in that case, should you use this as an RTT measurement or not? Should this be considered a sample RTT? And what they decided is that they are not going to do this. So the solution is that do not use RTT measurements for a retransmitted packet. Okay, so in this sort of a situation, you would just not use this in updating the timeout value. Okay, so what you are going to do is, you will only take the sample RTT if the packet was transmitted the first time and you got an acknowledgement for it. Okay? So this is another solution. Okay, so this is about how the RTT is measured in TCP. So we can move beyond this, and let's talk a little bit about congestion control. So this is a very tricky situation which we have to deal with TCP. So you have the sender, and this is the internet, and this is the receiver. So TCP is communicating with the sender is communicating with the receiver. So the receiver can send some explicit information back, right? It sends back acknowledgements and so on. But TCP is not talking to any of the routers in between. That was what was done in the original internet, and now we realize maybe if there had been some communication, it would have been better. But that was the design, and we have to live with it. Right? So what they said is that this is a military network, and this network might go down at any time, it might fail. And TCP has a lot of state information. It remembers what was the packets that I sent, what were the acknowledgement numbers, and so on. And that state information should not be stored in intermediate routers because they were assumed to be unreliable, it could go down. So they said all the state information is pushed to the edge nodes, and TCP is essentially now a very complicated protocol, but it sits only at the end nodes, and then intermediate nodes don't care at all about transport here. Okay, so TCP doesn't get explicit information from the routers. It doesn't know if there is congestion or not. Okay, where it can get congestion information about is at the receiver. So the receiver has some buffer So let's say this is the buffer, and let's say that this is the total size is max receive buffer. So in this particular case you can get some feedback because what's going to happen is you're going to keep filling up this buffer with data as it comes in, but your application has read only up to this point. So application has read up to this much. So how much space do you have left in the buffer? Okay, so this is unread. So the space left is this much. Let me put it in this color. Okay, so this is actually a circular buffer. So what will happen is that after you finish writing here, you can go back and start writing from the beginning. Okay, so this part is unread. So what happens when you have congestion at the receiver? When you have congestion at the receiver, that means that the application is not able to read the data fast enough, because of which this space left decreases a lot. Okay. And of course this information about the remaining space left in the buffer, this is at the transport layer. This can be explicitly given back to the sender, because after all the receiver and sender are communicating with each other. Okay, so this information is sent in the field called advertised window. Okay. So we can take care of congestion if it's happening at the receiver explicitly, because this information about the remaining buffer space can be sent out. But if congestion is happening at a router in between, there is no explicit communication between the TCP and these routers. Okay, so TCP tries to infer that congestion is taking place here, and that is a difficult task. Okay, so there is something called explicit congestion notification, ECN, but it's usually not used much, okay, where routers can actually set some bits in the packets, right, as it goes through if there is congestion. Okay, but we'll ignore that for the time being, and we just assume that the sender has to infer that congestion is taking place. So first let's finish off this discussion and say how we deal with this, and essentially this is called flow control, and this deals with congestion happening at the receiver. So how do we solve this? Well, there is an advertised window field in the TCP header. And that is set equal to the space left in the receive buffer. Okay, so the receiver knows exactly, it knows how much the application has read, and it also knows how much has been written over here, right, into this particular buffer. So it's going to give that information back, okay, in the form of this advertisement. Okay. So what the sender does is the following. So sender has something called a window. This is the TCP window, and the window is equal to the maximum amount of data that you can have in the network which has not been acknowledged. So maximum amount of data in bytes which is outstanding, and this means it has been sent into the network but not acknowledged. Okay, so this is going to essentially be used to do congestion control. So how is this really important? So suppose round trip time is, let's say, is almost the same. Let's assume it's almost constant, right? Is just for discussion's sake. Then what is your data rate? So you're sending, so the sender is sending out data. So this is the sender and this is the receiver. So this window is saying that I can send out a certain amount of data, and this was the maximum amount of data I can send out even if it's not acknowledged. So what I would do is I would send enough data corresponding to the window. This is, let's say, the window in bytes. Okay. And let's say I send it out at one shot. As we see later on, it's not exactly like this, but suppose the window size is something and I sent out that many bytes. I'm not allowed to send more than this out into the network because window represents the maximum amount of data that is outstanding, and I've sent it and I haven't got an acknowledgement. So now let's say I get back acknowledgements. Okay, I get lots of acknowledgements for this data. And maybe let's assume, let's say that this axe came back at one shot, just to simplify things. So what is my effective data rate at which I am sending over here? So I am sending out window amount of data, and this is roughly one round trip time. Okay. So data rate that I am sending out is roughly equal to window divided by the round trip time. Okay. So by controlling this window, effectively I am controlling my data rate which I am sending into the network. Okay. And depending on whether there is congestion either at the receiver or at some intermediate router, I want to increase or decrease this window size. So what we want is that we want window to be definitely less than the advertised window. And why is that? Well, just think about it. So this is the remaining amount of space that is there, what I am showing here, over here, this part and this one. That much space is there in the buffer. If the sender sends out more than that space in the buffer and it reaches the receiver, and let's say the application hasn't made any progress in reading more data, then some of that data is going to be discarded because there is no space in the buffer to keep. Okay. So window is sort of the maximum chunk of data that is out there. So that chunk I want to be able to store in my receive buffer whenever it arrives. Right? So the window has to be definitely less than the advertised window. Okay, so that's one thing that I want. So this is ensured to take care of flow control. So there is something else which we will calculate called congestion window. So how to deal with congestion? At routers in between. So we calculate something called congestion window. This is something inferred. We don't know exactly what are the, what's the state of congestion at the routers, but we infer it. We can calculate we infer the congestion and then we set this value appropriately. And to handle both flow and congestion control, what we do is we set window is equal to the minimum of advertised window and the congestion window. So we ensure that we are not congesting the receiver from this term, and we ensure hopefully that we are not congesting the network by ensuring that the window is less than this. Okay. So in practice, of course, what are these windows going to be? Well, it all depends on what is the data rate possible in the network, right? And it depends also on the round trip time. Okay, so if the round trip time is large and the allowed data rate is quite high, let's say you have tens of gigabits per second, then the window size would be really large. But if the round trip time is small, let's say you are connected to another machine in the lab, so the round trip time is extremely small, and so even if the possible data rate is very high in gigabits per second, it's possible that the window might be small. Okay, so it really depends on both the delay given by this round trip time and the possible band. So effectively, window is roughly equal to the data rate possible multiplied by the round trip time. Okay. And this product is sometimes called the delay bandwidth product. So if your delay bandwidth product is high, so we are calling this data rate essentially the bandwidth. The delay bandwidth rate is high, then you can expect a large window. Okay? But if one of them is small, then of course the window is going to be small. Yeah, and So you can think of this delay bandwidth product as sort of the pipe available. So suppose you model this network as a pipe, which you're trying to fill, let's say a water pipe between the sender and the receiver. So you're trying to fill up this pipe with data, and so you're going to have the window is going to be large if it's a long pipe. So even, the diameter is like the data rate, and the length corresponds to the latency, which of course we are saying is related to the round trip time. Okay. So if this is the situation, of course it depends how much water can you fill in here, right? That is sort of going to be the window size. In another scenario, you may have a very fat pipe, in which case it means your data rate is high, and of course there is certain amount of latency. And sometimes it may be that your data rate is pretty high but the latency is low, and in this case your window size might still be small. Okay, and so window has to fill up sort of the volume over here. Okay, and okay, so it really depends. You may have a fat pipe which is short because the latency is small, or you may have maybe a situation where the pipe is small, meaning your data rate is low, effective data rate is low, but the round trip times could be quite large. Okay, so the volume here in this sort of a situation is analogous to the window size. Okay, so you'll see these sorts of figures in your textbook and other maybe articles. So effectively the window is going to fill out, your goal is to use a window size which is going to fill up this pipe. So how exactly to set this congestion window, we'll look at in a future class.